I will derive the average speed of a gas particle in a three-dimensional space. In another video, we learned this equation, the probability of finding a particle moving in the x direction at a speed between Vx and Vx plus dVx. This dVx is the exact differential, it's infinitesimal. This probability is equal to the normalization factor A multiplied by, this is a Gaussian function of Vx times dVx. This normalization function is equal to the square root of 2m over pi kBt. It's derived in another video on the calculation of the average translation energy. So we're going to use this equation here, and what we're going to do is we're going to first visualize the speed in the three directions. It can be Vx, it can be Vy, it can be Vz, and then we introduce the directions. You can have positive Vx or negative Vx, positive Vy and negative Vy, so you have three different directions, and the velocity of the three-dimensional particle is going to be like this. So V, the velocity, is Vx times the unit vector of direction x, y, and z. And what about the length of the vector? The length of the vector is, this means the magnitude of vector is equal to Vx squared plus Vy squared plus Vz squared. And our goal is to calculate the average speed. And how do we calculate the average speed? Well, you might just think of something like this. You know, V can go from 0 to infinity, and then multiply by the probability of V, and then dV. To be more precise, this is actually probability density. And this whole thing is the probability of finding a particle moving at the speed between V and V plus dV. Alright, so I'm going to do this, but how about the probability of finding the particle moving at speed between V and V plus dV? We'll have to use this equation, and we'll have to do a transformation from the Cartesian coordinates to the polar coordinates. So again, the average speed is here. It's from 0 to infinity. V times the probability of this. However, we have three directions, so what we need to do is we actually need to do something more complicated. First, we're going to look at the magnitude of Vx, Vy, and Vz. They can be from 0 to infinity. And then we put V here, and then the probability of having speed V is actually this term for x direction multiplied by a similar term for the y direction and then z direction, so it's going to be a to the power 3. And then we have this Gaussian functions. In three directions combined to be this guy. If we allow Vx, Vy, and Vz to be negative numbers, we can do so by realizing the symmetry of this V, the speed, with respect to the x-axis, y-axis, or z-axis. Mathematically, we say V is an even function of x, y, and z. So basically, this space from 0 to infinity for x, y, and z is only 1/8 of the total space. So this is the total space in which Vx, Vy, Vz can be positive or negative. So 1/8 of that, and then we do this. dvx, dvy, B, Z. All right? Next step, we will use our knowledge in multivariable integral calculus to convert this Cartesian coordinates to the spherical polar coordinates. I will not show you the derivation here. But I want you to imagine the Earth. You have the latitude with a span of 180 degrees and the longitude with a span of 360 degrees. So I'm converting the three limits for Vx, Vy, Vz to the limits for R. Well, in this case it's not R, it's the V, theta, and phi. Over here, dvx, dvy, dvz, the volume element is converted to v squared sine theta, dv, d theta, and I have space for d phi, so I'm going to write it here. It's not too difficult to integrate this triple integral after you separate the variables. You see theta here, theta here, theta here, we're going to integrate this. You see phi here, you see phi here, we're going to integrate that, and then we're going to integrate the function of v. So it's going to be 1/8 the integral of theta from 0 to pi sine theta d theta, and 0 to 2 pi. I think we're going to just integrate the phi, that's easy. Finally, from 0 to infinity, that's the limits for the speed. And we have v to the power 3 here, and a to the power 3, I'm going to put a to the power 3 in front of the integral because it does not depend on v or theta or phi. This a is actually a constant given the mass and temperature. So we'll just evaluate this integral. Okay. The integral of sine theta is negative cosine theta. And this guy is very simple, so I'm going to just put 2 pi here. And over here I'm going to do some transformation. So I'm going to just decompose v to the power 3 into v to the power 2. And over here I'm going to have v dv here. And the reason we have v dv is v dv equals half dv squared. And therefore, well, over here we can plug in cosine pi and cosine 0 here. So cosine pi is -1, negative 1 is positive 1, cosine 0 is -1, so we have that. And over here there's a half, so I'm going to put a half here from 0 to infinity. And before we write out this function, we're going to set q equals v squared. Q is just dummy variable. So it's going to be q and e to the power negative m2 kb dq. And then this guy becomes dq. Actually it's half dq, but we put the half here. And we look at this 2, they cancel. There's another 2 here. This 1 minus -1 is 2. So we have 4 on the bottom, pi a cube. 2, that's 4 on top, and 2 and 8 on the bottom, so it's, yeah, that's correct. Okay, we're going to further transform this. So we're going to say maybe S equals m2 k b t times q. The only reason is we want to simplify this this exponential function. Actually, why don't we just put a negative sign here to make everything easier? If we put a negative sign here, this exponential function is just e to the power of s. And then q equals negative 2 k bt over m times s. So that's very straightforward. I'm going to plug in this to here and to here, and then we get this coefficient twice. That's squared. And then we have oh, pay attention here. Since we said s equals negative something times q, the lower limit is still 0, but the upper limit is negative infinity. And s e to the power of s ds. All right. It's actually fairly straightforward to evaluate this. I'm gonna do this on top. I'm going to combine this too. And then I'm going to use the product rule. So basically you're looking at two integrals. The first integral is the integral of the exact differential of the function. The result is this function itself. It's s times e to the power of s. You plug in s equals negative infinity, you get 0. You plug in s equals 0, you get another 0. So basically this one is just 0. How about this one? This one is very simple. It's just e to the power of s. And again, there's a negative sign here. So what you can do is this. You can change this negative sign to positive sign by switching the lower limit and the upper limit. Okay? And then the result is e to the power of 0 minus e to the power of negative infinity, which is 1. So this whole thing is just 1. This whole thing is just 1. And the result is going to be, oh, I accidentally put this here twice, so maybe we should erase this. So in the end, it's going to be just simple algebra. We just need to multiply this term and this term together. And we have 2 squared here, right? So it's going to be kbt over m squared times pi a to the power of 3. We know what a is. A is over there, so I'm going to erase this line and some other lines to make it easier to see. It's going to be kbt squared multiplied by pi multiplied by pi kbt. I'm copying this here. Alright, so pay attention to this guy and this guy. They are inversely, well, they're just the inverse of each other. So basically it's just 2 minus 3/2. And then times pi times, well, over here you got the square root of 8 to the power of 3, that's 8. And then this is also pi cubed. Well, it looks complicated, but we can further simplify this. Equals, we're going to move this pi inside, so it's going to be, we're going to put this in the square root sign as well. I'm going to move this inside.